Okay, hi guys. So now we'll be discussing on the irreversible process. So let's get started. Irreversible process. Okay. So let's suppose we have this case when we have some gas molecules filled in chamber A, and in chamber B we have, let's say, vacuum. Okay. So P external here would be 0. Okay. And what will happen is this gas which is present in chamber A will expand. Okay. So this is an example of expansion against vacuum. Okay. So where P external would be equals to 0. So once the gas starts expanding, it is impossible to again restore the gas back into the initial state. Okay. So as P external is equals to 0, work done by the gas would be equals to 0. Okay. And as this we are discussing for the idle gas, so for an idle gas, delta U is just a function of temperature, and in this case temperature of the gas is not increasing, hence delta U would also be 0, and we know that delta U would be equals to Q plus W. As W is 0, delta U is 0, this implies that heat exchange by the system from the surrounding or from the surrounding to the system would be 0, and similarly delta H would also be 0. Okay. Next, let us see the expansion and compression of a gas against some pressure. Against pressure. So here P external would not be equals to 0. Okay, so we can write that delta U would be equals to 0 and delta H would also be 0, but work done would not be equals to 0. Okay, so we can write dW is equals to minus P external dV. So I hope you remember that this all we are doing at t delta t equals to 0 or t equals to constant. This is a isothermal irreversible process. Similarly, this is isothermal expansion and compression against external pressure. Okay, so delta t equals to 0. Hence, as delta t is equals to 0, delta U and delta H would also be 0 because we are considering idle gas scenario. Okay, so we can write delta W would be equals to minus P external, or rather dW would be equals to minus P external dV. Okay, so we can write that P external is P internal plus minus delta P. So we can write that dW would be equals to, as dW equals to minus P external dV, we can write that W irreversible would be equals to, again put the value of P internal plus minus dV here. So again we will be getting delta P delta V term here, so we are just neglecting that, so we are simply writing minus P delta V. Okay, so again for W irreversible we can have, or we'll get minus P and RT upon P2 minus, so rather this can be written as minus P minus P delta V2 minus V1. So V2 minus V1 can be written as nRT upon P2 minus nRT upon P1. Okay, where P1 and P2 are initial and final pressure of gas. And we can write that in complete expansion or um, compression process, P external would be equals to P P2 here. Okay, so this is in case of complete expansion or compression. Okay, next let us see single stage expansion. Okay, so we can write P1 equals to 4 atm, and let's say P2 equals to 1 atm, which is also, let's say, P external. So the PV graph would look something like this, in which we have P on y-axis and V on x-axis. So initial pressure was 4 atm, something like this, and then it was dropped to 1 atm. Okay, so external pressure was this P2 or P external. So from this it drops to from 4 it drops to 1, and then it expands, so from V1 to V2. So A point to B point, A point is P1 V1 and B point is P2 V2. So this is the case for single stage expansion, and in case of double or n stage expansion we'll have different type of graph. Suppose we have a double stage expansion, so the graph would look something like, so suppose we have double stage expansion. So the graph would look something like this. We have P and V here. So in step 1 we have P external 1, which would be equals to, let's say, 2.5 atm, and step 2 we have P external double dash, which is, let's say, 1 atm. So we are compressing, or rather expanding the gas in 2 stages. So we would have something like, this was initial P1, this was P external dash, and this was P external double dash. Okay, so first gas is rather expanded at P equals to P external, and then it is again, the pressure is further reduced from this V1 dash till V2. So work done would be something like this. Again we have point A and point B. Coordinates are P2 V2 here and P1 V1 here. Okay, next let's see n stage expansion. So n stage expansion is also rather falls into the category of reversible expansion. Okay, so let's see how this goes. So again we have a PV graph. Again we have point A P1 V1 and point B P2 V2. So in n stage compression, or rather expansion, we have again, it actually breaks down the path from V1 to V2 into small chunks or small n chunks. So in this case the work done would be maximum. So maximum work done by the system in reversible process. This is reversible in the sense that we are just dropping at any point of time pressure and volume, or rather we are dropping pressure just dp and we are also increasing volume just dv. So it can be reversed also at any point of time. But in the case of double stage expansion or triple stage expansion, it was not possible because we are suddenly dropping the pressure from 4 to 2.5 and from 2.5 to 1. So again reversibility is lost. And in the first case we are suddenly dropping the pressure to 1/4 of its value, hence again this is an example of irreversible process. So in this case the area under the curve was only this one. In this case area under the curve was slight bit more, and finally in the reversible process area under the curve would simply be covering whole of the graph, area under the curve. Okay, so in gas expansion we can write that mod of V reversible or W reversible would be greater than mod of W irreversible. Okay, so with this we come to the end of this lecture. In the next lecture we will be discussing on single stage compression, double stage compression and n stage compression, and then we'll look into adiabatic process. So till then, good luck and goodbye.